Hey everyone, so in this video, I'll cover the basics of Coulomb's law, which is a law that essentially attempts to calculate the electrostatic force between a set of charged particles, which could be a push or pull in a certain direction, dependent on whether the charged particle being studied is being attracted to or repelled from another charged particle. The electrostatic force of attraction or repulsion is similar to that of the poles of a magnet interacting with one another. So what formula should we use when computing the electrostatic force between two charges? We need to get comfortable using the formula associated with Coulomb's law, of course. It states that F is equal to K times Q1 times Q2 divided by R squared, in which F represents the electrostatic force between any two charges and is measured in newtons. K represents Coulomb's constant, which is 9 times 10 to the 9 newtons times meter squared divided by Coulomb squared. Q1 and Q2 represent the charge of charges 1 and 2 measured in coulombs. And R represents the distance between the centers of the two charges measured in meters. One huge thing to remember is this conversion. 1 microcoulomb is equal to 10 to the minus 6 coulombs. So it's very imperative that we know that, because if a problem gives us the units in microcoulombs, we need to make sure we can be converted to coulombs, because the Coulomb's law formula is only conducive to the unit of coulombs, not any other. Like, it can't be like microcoulombs, picocoulombs, nanocoulombs, stuff like that. So keep this conversion in handy. Now let's do a few practice problems to apply this formula. Number 1. Calculate the electrostatic force acting on charge 1 due to the presence of charge 2, given that charge 1 is positively charged and charge 2 is negatively charged. So let's begin this problem by illustrating what it has given to us. Here's charge 1, here's charge 2, and here's charge 1's magnitude of negative 42 microcoulombs. Here's charge 2's magnitude of 125 microcoulombs. And they're separated by a distance of about 6.2 meters. And since they're oppositely charged, they're going to attract one another, as we can see. And, okay, so in this case, since the problem is asking us to find the electrostatic force acting on charge 1 due to the presence of charge 2, charge 1 is going to feel a force that's going to pull it in the positive x direction, or towards the right, because it's being attracted to charge 2. So it's going to feel a force that's going to push it towards charge 2, right? So it's going to be pulled in the positive x direction, right? According to these arrows. So that's how we would use it in our vector notation. So we would use the positive x direction to represent our answer in vector notation once we calculate the magnitude. So once again, we chose the positive x direction when computing the force in its vector format, since charge 1 was being pulled towards the right due to the attractive force by charge 2. Remember, opposite charges always attract. So now we can plug the values into the Coulomb's law equation, which states once again that the electrostatic force between any two charges is equal to the Coulomb's constant times charge 1 times charge 2 divided by the distance between them squared. So let's remember to convert. So negative 42 microcoulombs is equal to negative 42 times 10 to the minus 6 coulombs. And 125 microcoulombs is equal to 125 times 10 to the minus 6 coulombs. Alright, so plugging all this information in, for K we'd plug in 9 times 10 to the 9 newtons times meter squared divided by Coulomb squared. And for Q1 we'd plug in 42 times 10 to the minus 6 coulombs. And Q2 we'd plug in 125 times 10 to the minus 6 coulombs. And R we'd plug in 6.2 meters. Alright, so simplifying this equation a little bit, we can see that if we were to multiply 42 times 10 to the minus 6 coulombs by 125 times 10 to the minus 6 coulombs, we get approximately 5.00 times 10 to the minus 9 coulombs squared. And if we were to square 6.2 meters, we get 38.44 meters squared. Notice how the meter squared and the coulomb squared cancel out, as they're both in the numerator and denominator of this problem. So with that said, they'll just reduce to 1. So all we're left with is Newton. Which is good, because that's what force is measured in. Electrostatic force is measured in newtons. So that's good that we have that unit. Alright, so just simplifying this a little bit more, we have 9 times 10 to the 9 newtons times 5.00 times 10 to the minus 9th power, all divided by 38.44. Plugging this ratio into our calculator should yield a value of approximately 1.17 newtons. And remembering that we had chosen the positive x direction, since charge 1 was being pulled in that direction towards charge 2 due to the attractive force, we can denote this as 1.17 newtons in the positive x direction, if we were to use vector format. Alright, let's do another practice problem and just get used to this formula a little bit more. Number 2, calculate the electrostatic force on charge 1 due to the presence of charge 2, given that both of them are positively charged. So let's illustrate it once again. So we have, here's Q1, here's Q2, here's charge 1's magnitude, which is 9 microcoulombs, charge 2's magnitude, which is 16.5 microcoulombs, and they're separated by about a distance of 1.3 meters. And so in this case, since they're oppositely charged, right, they're both positively charged, they're going to repel one another, right? So they're going to be like pushed in opposite directions. Like if you were to bring them close, they're just going to go in opposite directions. They don't want to they don't want to have any contact with each other, right? So here's the vector showing the directions in which they point. So Q1 would be pulled in the negative x direction, going to the left, and Q2 would be pulled in the positive x direction, going to the right. So in this case, since the question is asking, or the problem's telling us that calculate the electrostatic force on charge 1 due to the presence of charge 2, we can see that charge 1, shown here in the maroon color, it's gonna be pushed towards the left, right? Because it's being repelled, right, from Q2. Since they're oppositely charged, it's gonna be pushed to the left. It's gonna go towards the left, right? And the left is the negative x direction. So when we find our answer in vector notation, we would denote it with the negative x as our direction. So yeah, with our magnitude, we would just add the vector component of negative in the negative x direction. So yeah. Alright, so once again, we chose the negative x direction when computing the force in its vector format, since charge 1 was being pushed towards the left due to the repulsive force of charge 2. And remember, like charges always repel. Alright, so now we can plug it into Coulomb's law equation, which states the electrostatic force is equal to K times Q1 times Q2 divided by R squared. Remember to convert, once again, 9 microcoulombs equals 9 times 10 to the minus 6 coulombs, and 16.5 microcoulombs equals 16.5 times 10 to the minus 6 coulombs. So plugging all this information in, K would be 9 times 10 to the 9 newtons times meter squared divided by coulomb squared, and Q1 would be 9 times 10 to the minus 6 coulombs, and Q2 would be 16.5 times 10 to the minus 6 coulombs, and R would be 1.3 meters. So simplifying this a little bit, 9 times 10 to the minus 6 coulombs divided 16.5 times 10 to the minus 6 coulombs would yield a value of 1.485 times 10 to the minus 10 coulombs squared, and squaring 1.3 meters would yield a value of 1.69 meters squared. Notice that once again the coulomb square and the meter square cancel each other out, as they're both the numerator and denominator of this expression. So now we're just left with the Newton, which is a good thing because that's what, like we said before, electrostatic force is measured in. Alright, so just rewriting this a little bit more, we'll have the force on charge 1 due to the presence of charge 2 is equal to 9 times 10 to the 9 newtons times 1.485 times 10 to the minus 10, all divided by 1.69. And if we were to plug this into our calculator, we should get an approximate value of 0.79 newtons. But like we said, due to charges 1's force that's going to pull it in or push in the negative x direction, we need to add that negative sign if we were to convert this to a vector. So in vector form, this would be negative 0.69 newtons. Yeah, so it would be 0.79 newtons actually in the negative x direction. That's another way to say it. Alright, so that's all I have for today. So thank you for watching, and I hope this video helped. And if you want to learn more on Coulomb's law, check out the other videos in this playlist. So have a great day.